this lesson, you'll come away from this going, hey, there are some really, really easy techniques that give really good results where even if you're not really confident about statistics, you'll still come away from it going, hey, I get this. This is really simple. This is really obvious. So let's do a quick little reminder. So my usual import all the magic things. Oh, that's the second time that's happened. And I always put up this motivational picture, which says, this is the kind of thing that data scientists actually spend their time doing. 60% of the time, according to a study done in 2017, data scientists are just doing very simple regression problems. And they're simple because you know the techniques. We'll talk about clustering later in the course. We've done a bit of visualization. We'll continue to do more. We will cover decision trees and random forests. And then way, way down, we start looking at, yes, doing descriptive statistics of things, and various others get lower and lower on the list until a very, very tiny percentage of time you get down to people doing deep learning kind of activities. Right, so quick review. Here's what we were doing. You have a model and it makes some predictions, and you ran it over the training data, and there'll be some errors. And for each point, you look at the sum of the squares of the differences between what was predicted and what it's supposed to be. Sum up the squares of those, and you're looking for the line that makes it the smallest sum in the training set. And then what we did is we looked at how did that work on a test set. And we saw that, you know, for ordinary least squares, it just didn't do all that good a job on the Sacramento data set. But when we introduced lasso, we did a little bit better. I've got some really gobsmackingly ugly code here. I'll briefly go through it, but don't be too worried by it. This is a function. It takes a couple of arguments. You hand in like the y test value, you give it the model and where to draw things and whether to draw some error bars, and it'll draw a scatter plot. It'll take the predictions from your actuals and try to make some sort of prediction of it. We'll draw that in red, calculate the squared differences, go one by one through the predictions, and draw up some pretty line if required, and calculate what it is and draw up a sum of squares difference. Now, let me just give you a first example. And so here's my example data up here. And then I'm giving 4 linear models. So this part, if I don't rush through it, you'll all feel very comfortable with that. I'm creating a series. Here's the data in the series. Here's the index to that series. And so I've created a pandas series with, if you look at it, very evenly spaced points and a bunch of data that's a bit all over the place. Then I create some subplots. So I've got 2 by 2 subplot and fiddle around with the spacing of it. This next line should be okay. Create a linear regression model. The thing that you'll probably find a little bit weird is these next 2 lines here. When you're doing training on a linear regression, the fit method populates coef and intercept. But here, just to illustrate some really bad lines, I have, instead of doing a fit, I've actually just assigned them. I've said, I want the coefficient on X to be 20 and I want the Y-intercept to be minus 40. And I did the same thing a couple of times. So I've got 4 different lines here. And when I run it, I get a terrible, terrible error message because I forgot to do something. I forgot to run the previous cell. And I get this plot that you can see on screen here. So here was my data, 1, 2, 3, 4, 5, 6, 7, 8 in the x-axis. Here's the actual values. You can see them sort of plotted around. And on my first line, you can see how bad the error was. And then on the second line, you can see how bad the error was, and third line, fourth line. And you can see if you've got really, really good eyesight, and you zoom in really, really far, the sum of squares difference on this line was 4246. And this line's a bit better, and it's got a sum of squares difference of 326. And this line was absolutely gobsmackingly terrible, and it's got a 126666. So we can say this is a better line because the sum of squares difference is smaller. And instead of manually doing things, I can go and do a fit like I just did before. And you know, this is the best possible line. It's the one where the sum of squares difference is only 278. That's the best possible ordinary least squares regression line. That's the one it's going to choose. Let's have a little quick quiz, and I'm not sure how to do these easily. I did have that polling. Let's see if I can make this poll work quickly. Should have planned this up, and I'm creating a new. It gave me poll 1, but I'm going to change that. Everybody fall asleep for 1 quick second while I make this poll. And assuming I got this right, let's take it away on this poll. Save and that's not actually running through the Zoom session, is it? There we are. Let's launch question number 1. Took me ages to get there, but I got there in the end.
That r square comes up as -2 there, so it's actually r squared.
Yes, thank you. That came up really badly, didn't it? I'm going to have to edit that poll and fix it. But imagine the -2 said r squared, and yes, and that's indeed what the ordinary least squares regression is doing. It's trying to minimize the squares, get the least squares that you can. Next kind of easy question. And I'll just end that poll there and see if I can make another one without without dying too badly. Is I should be able to ask true or false. Madly doing this in time. Polling, give me number 3. That, again, you can sort of see the question on screen, even if the poll question has sort of fallen apart kind of badly. Should we go true and false? Ordinary least squares only works when you have 2 dimensions, a 1 dimension of y and a 1 dimensional of x. And I'm getting lots and lots and lots of people correctly answering that that's false. You can do least squares where you have multiple dimensions. In fact, we've just done that in the Sacramento house. We had 3 columns. We had the square footage, the number of bedrooms, number of bathrooms. So we had 3 dimensions on X and 1 dimension on Y. So that one's false. And the last poll question, which I'm not going to bother putting in the poll because I'm kind of frustrated using that polling tool, is the line found by minimizing R squared affected much by outliers? And since you've had like 2 easy questions, this is obviously the nasty question. And we've saw that in all sorts of places, like the 8-bedroom house in Sacramento. It would be very hard to predict. So why do we like this? Why do you find lots of data scientists using R squared, and why do you see lots of statisticians? One of the rather awkward ones is because it's a unique answer. And so if I'm a university professor and I want to teach about linear regression, I can set an assignment where you have to calculate the ordinary least squares regression of some particular set of data, and then I can mark the answer right or wrong. And that, of course, is convenient because it makes the marking process a whole lot easier. It's also nice because you can actually just do some calculus and you can find what's called a closed form formula for calculating it out. And it has a nice property that it makes sure that big mistakes are small. There are some really fundamental problems though. Problem number 1, if you have one absolutely massive outlier, then ordinary least squares will try to minimize the square of the distance to that point. So do you remember house number 703? If we had left that in the data set, then the ordinary least squares regression would have tried to minimize its mistake when it's trying to predict a house at minus $200,000. So the line of regression will have to pass closer to minus 200,000 than it otherwise would have. Now, minus 200,000 squared is 400 million. It's a very, is that right? No, it's 40 billion. And let's see if I can get that correctly. Indian, that's 400 crore, something like that. It's a really big number, so therefore it's trying to minimize that. It has some other assumptions. It assumes that the X values have no errors in them. So did we correctly measure the number of square feet in the house? Well, probably not, because like there will be, you've got to go and get the tape measure out and you could make mistakes in that and you've got to round it off. And that's one of the assumptions, that it doesn't have error. And also it doesn't really correspond to what's the actual cost to the business of you getting one of these things wrong. So it's actually quite rare that I'm going to minimize R squared is the right thing to do. So what should we do? Well, there's 2 things that we do quite a lot of. The one that I introduced to you on Monday is the idea of regularization. And this is good when you have a small number of data points, but you have a lot of information about each data point. So examples where you see this is, I might only have 900 houses in the data set, but I've got 500 different attributes about the house. What it's made out of, how far to the nearest fish and chip shop, how far to the school, how far to the mosque, how far to the water, how far to the nearest highway, the length of time it takes to drive into the city. You can create a huge number of columns in your data frame and a small number of rows. And if you've got that kind of problem, then regularization works really, really well. And you can see that we're coming close to that in the Sacramento data set, where we didn't have a huge number of data points. We only had 600 that we were working with. And so making sure that we got the simplest model, the one that didn't focus on unnecessary columns worked reasonably good. The other possibilities we can do is what's called robust regression. And this is when you've got a noisy data set. So there's all sorts of things that you aren't capturing, you don't have information about it, that affect the value. So there's all sorts of things in that data set for Sacramento housing that we didn't capture. So is this a slum? Is it a high crime area? Are there any jobs nearby? We didn't capture any of that information. And so there will be lots of things that affect the price that we can't see. So there's a lot of noise. Well, let's launch into that. So this is trying to create a linear model that's best in some way without being sensitive to outliers and noise. Right, I'm going to draw another one of these fairly complicated piece of code. Yeah.
One question. So, I mean, I could understand the outliers part, but the noise part is not clear to me. So what you're saying is that the data doesn't have many features which, which could impact the price, but we don't see it in the data. So are we calling the lack of that data as a noise?
Yeah, so the effect is that if I'm trying to predict this particular two houses that have the same number of bedrooms, same number of square feet, same number of bathrooms, there can be a lot of variance in them. And so it looks like noise. Actually, it's not noise. One of those houses has an immaculate garden and is in the safest place in all of Sacramento. And the other place is next door to a rubbish dump and is surrounded by drug dealers. Those are going to be very different results, but we won't be able to use that information in prediction because we haven't got that information at hand. So it manifests itself as if it's noise. It's like somebody has just added a random number to the price without telling us how or why. So it looks like noise. It probably isn't, but that's what it looks like. Is that helping? Yeah.
Yes, okay.
Okay. Let's draw a line with an obvious problem. So let's say we've got this data set on the left here, and we're trying to make a prediction from it. And like we're doing fine on these data points here if we drew a line straight through it, but we would definitely get this line wrong. Now, whether that point is an outlier or whether there's just a whole bunch of noise, if you try to minimize the sum of squares, this is the line you're going to get. And I tend to think of this in terms of sort of the line here wants to minimize the sum of squares. So it wants to try and nudge itself up flatter and higher at the left-hand end in order to meet that point or be closer to that point. And so it's traded off. I want to get close to this point, and because that square distance is so huge, therefore it's willing to lose a lot of penalty on these other points to try to get there. There's a phrase for what's going on here, and that is the error here is not heteroscedastic. I've been practicing that. The problem being there's not a normal distribution on either side here. We'll come back to talking about normal distributions again later, but this isn't. You've got a whole bunch of points on the left-hand side. If I stick my head this way, I've got a whole bunch of points on the left-hand side, a whole bunch of points on the right-hand side. But I've got 2 on the right and like 8 on the left, and the ones on the left are really close. Okay, let's talk about Professor Sen. Now, Professor Sen is actually from Calcutta, and he's still alive, and he was born in like the 1930s. And he came up with a method that was also simultaneously come up with by a Dutch professor called Dr. Theil. And so that is Dr. Theil, being Dutch. That's why you don't have the TH, so it's not th. And Professor Sen is, well, just Theil-Sen, I think it was. And the Theil-Sen method is really kind of simple. I've got my data set. I will pick a pair of points at random, and I'll draw a line through them and keep track of the gradient. Then I'll do that again and again and again and again, maybe 25 times. And then I'll sort the gradients, sort the lines by gradient, and I'll then pick the one that has the middle gradient. And if you think about this, this is going to be quite a good line. It's not going to be overly affected by outliers. If you have one outlier and sometimes you pick that point at random, that won't matter too much because the median line is still going to be very similar. Most of the time, the median lines are going to be the ones that are pretty good. And it will go through a fair number of points and it will be roughly indicative of the data set. The other nice thing about this, and that's actually why Dr. Theil and Professor Sen did this, is, okay, let's do it 25 times. And that's going to get you a pretty close answer. Or I could do it 250 times and that's going to get me an even more precise answer. Or I could do it 1,000 times or 1,000,000 times. But did you notice I didn't actually need to know how many data points there were in the data set? So you come up to me with a 10 million data point data set. I do 25 pairs randomly selected from that 10 million data point data set, and I will give you a pretty good estimate of a good line of best fit through that data set. It's quite remarkable. The way I like to do this, and I've never successfully done this remotely before, but let's just see how we do it, how we go. Normally I do this as a group activity. So if I turn off the share here and point the camera down at the table, that's a bit fuzzy at the moment, so I'm going to fiddle around with the focus and hopefully get this to work. People often find it really helpful to just watch it as it happens, because you get a clear sense of what's going on. So I've got 66 data points here. Let me just see if my camera is in range. So if I want to go further this way. It's kind of funny watching the screen because it's upside down from where I'm looking on my table at the moment. Okay, so let's spread these data points out, and I'm going to try and come up with a line that goes through this data. So sorting it out. Let's make some outliers. Let's have point number. It's actually a bit wide. There you go. Can you see that we've got a line happening here? It's a pretty straight line. If I move my finger along it, I'm starting at one end, moving up to the other, and I'm getting a line going through there. So if I had some extreme outliers, let's put 23 over here, and some more outliers. Let's put a really weird outlier. We're going to go up there, and another outlier. Just going to figure where I want to put it over. Just trying to get it in camera. There you go. I could put some more noise in here if I wanted to. So I've got my y-axis being up and down the screen and my x-axis being across the screen. And I want to be able to predict for a point, a certain number of pixels across the screen, across X, where is it on the Y? Well, let's do the Theil-Sen method. So the Theil-Sen method says, roll some dice, pick a random point. Oops, pick a random point. So that's 31, which is down here. So coincidentally, that was at the very edge of the data set. That was just kind of, I promise you I didn't use loaded dice. And what's the next next point? It's 53. If anybody can see 53 really quickly, that would be helpful right now. I can't see it on my set here. Maybe it's hidden underneath something. 43, 52.
Below 32?
Below 32? What's that? 53, thank you very much. Okay, so let's draw a line between those 2 points, which I'm going to use my magic string here. And my next challenge is actually sticking this onto the table successfully. So I have 31 to 53. I'm going to put some blue tack on the table up about there and there. And then I'm going to draw a line through that. Everyone happy that that's going through 31 through to 53? There's 53 there, there's 31. Yeah, the angle on the camera makes it look a little bit odd, but that's okay. Let's do it again. Next pair of points. So 45, which is right up this end. I'm not sure if you can actually see it on the camera. I'll move the camera across a little bit. And there's, yet again, it happened to be right at the edge, which was kind of a surprising coincidence that happened. So I've got to do 45. And next, that's 43, which is that point in there. Okay, so let's go again. Let's grab the string and some blue tack. So I'm doing 45 through to 43, which would be a line like about that. Okay, let's grab the blue tack and see what happens. What happens is my fingers get really sticky and not much else. So we had a line going through 45 through to 43. Hopefully that looks about right. I'm not sure everybody can see that's going through 43 in there. I'll just move the camera back a little bit so that you can see what's going on. So I've got 2 lines through my data set here. And now I'm going to fake the next dice roll. I'm going to choose, so some random point here, 44, that's good. That's dead smack in the middle of the screen here, 44. And just to make things worst case scenario, imagine I was doing this and I then happened to roll 23. So I rolled, got it in the wrong spot, I rolled 23. And that's this line here, with this data point here, which is really far and away a ridiculously bad outlier. So I still have to do it. I had 44 going to 23. Oops. So I still have to make this line. And the nice thing about this is it's not actually going to have all that much of an impact on the Theil-Sen algorithm. At this point, if I stopped, I would be looking at the median gradient, and I've got one here, just move my hand in the right place, another one here, and then a third gradient that's completely different. So the median gradient is going to be one of these two. In fact, they're so similar I can barely tell them apart. These 2 lines along here, you know, the gradient is really, really close. So I'll just roll twice more. This time I'll be trying to do it as quickly as possible. 12 and 41. 12 and I know we had 41 somewhere before. Oh, 12 and 41. Oh, I've managed to get some really bad luck here. I'm getting some really, really ridiculously bad numbers. So 12 and 41. And we'll see what happens. It doesn't, this being Theil-Sen, it'll work itself out. 12 and 41. At this point, I've got an even number of lines, so who knows what happens next. And I've got 41 again, and let's see. Sorry, you couldn't see that on screen very easily. And 35. 35 is it's getting hard to see with all the number of data points on here. 35. If anybody can see it, much appreciated. 35. Might well be missing. 41 and 35. So I don't actually know where that is. So I'm just going to make it up. I'll pick another point and then we can discuss what happened afterwards. And so it was 41 to one of these data points down here. It doesn't really matter which one. The probability was it'll go where the most mass, the most density of points is. And so now I've got 5 lines. I've got line 1, 2, 3, 4, 5. So the Theil-Sen algorithm would say that this line here is the median line, which isn't quite right. I happened to get quite unlucky because I had my first faked one, and then my second line was quite way off. What would happen is if I run this a few more times, I'll eventually probably get a couple more lines in other directions. And I'd end up finding that it's one of these 2 lines that ends up as the median. That's the first time I've ever actually done a Theil-Sen by hand on 5 pairs where it didn't work out perfectly. Normally you'd get something like, say, that, and then you'd be going, oh yes, the median line is one of these core lines that captures the distance there. So let me pop back to sharing my screen again. There is another method that also works very well, and that's called the RANSAC method. And the way the RANSAC method works is you figure out some sort of measure of close enough. So maybe if you're doing the Sacramento house prices, you say, if I get it within $5,000, that's close enough. So then what you do is you pick a random pair of points and you draw a line through them and you count how many points were close enough to that line. Then you pick another pair of points and you draw a line and you count the number of times that they are close enough. And if it was better, then you use that one. Otherwise, you keep the old one. And you keep on going, you keep on going, and you try to improve and improve and improve. And you'll see that after a while, you're not really improving that much. And so then you say, well, that's it. That's the RANSAC line. So RANSAC's definition of the best line is the one that captures a lot of points, the one that models the data accurately most often, rather than say the least squares, which is saying the best model is the one that minimizes the distances. Or the Theil-Sen algorithm is the best linear model is the one whose gradient is closest to the median of all the possible gradients. Okay, let's do RANSAC now. This will either work well or it'll be a complete disaster. So I'm going to pull apart my blue tack and strings again, and I'll use the same data set, but I'm going to introduce more noise in the data set. So let's see how I go on this. So with Theil-Sen, I just had a few extreme outliers. With RANSAC, I'm going to go much, much worse. So, okay, I've got 31 up here. I've got a bit of room. Let me move the camera down. And I'm going to give you a core of a straight line. So just putting these into the camera, do you see we've got sort of a straight line happening here? It's straight line happening in the middle. And then I'm going to have just all sorts of random noise that makes it really hard to see that core straight line that's in the middle. A few of these are off screen, so let's move them around so they're on screen. Looks like there's a few data points that are out of screen, that one. Okay, I've got 45 up this end, that's a bit too far out. Just move these things down, there you go. So, there's definitely a linear relationship here. There is a straight line that's happening. That's from the points up here, 24, 36, and so on up to 45 here. They form a line. And then I've got a few other places where there are some sort of straight line linear relationships between X and Y. But if you looked at that data set just afresh, you'd probably go, hey, that's really, really bizarre. There's no obvious relationship. Okay, let's take it away. I'll roll the dice a few times and we'll see what we get. So 54, and what's the next point? 16. So 54 and 16. 54 and 16. I'm trying to find either of those. There's 16, so that's good. And 54. I can see 44. I can't see 54. There it is. Actually,
Seems
it's there.
next to 13, yeah.
Yeah, there it is. Okay. So this is going to be fabulously, fabulously good. So I've got my line happening here. And I have to have my measure of close enough. So I've got this very exciting paper clip, and I'm going to run the paper clip along the length of the line, and I'm going to count how many points I capture underneath the paper clip. So I start up at, say, this end. So just off screen, there's a 31. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Looks like I passed through 15. So Prashant or Patrick, can you put like 15 in Slack? Because we just need to remember what that was. And that first line was 15. Right, let's do it again. And I've got 12 and 62. So 12 and 62. 12 and 62. There's 62 over there. And this is going to be a terrible line. So 12 and 62. So I take my wonderful paper clip and I start at 62 and I ask how many dots is it going through, and I get 1, looks like it's going over 53, so I'll call that 2. Looks like it's going over these ones, so catches 44 and 12, so that's 3, 4, 5, maybe about 5. Over in the Slack session, if somebody can put in a 5, thanks, Patrick. So that wasn't very good. That was actually pretty pathetic. So let's throw that line away. It didn't beat 12. And we do it again. And 31. And what's the next number? 11. And 11 is just beside the dice there. So let's do the same thing again. I grab the magic string and the paperclip. Oh, got to move the dice out of the way. And I count how many data points I'm going through. And 1, 2, 3, 4 at this point, 5, 6 maybe, 7, 8, 9, 10. So I got 10 on that line, but that's still not as good as 15. So I throw that line away. And I keep on doing this and keep on doing this. And if I'm really smart, what I do is I plot how many times I'm beating the previous value. And if I'm not beating it on a regular, if I'm not beating it, and I haven't beaten it for a very long time, then I just give up at that point and say, okay, well, this is the best line I've got. And so the output from the RANSAC algorithm on this data set would say this line is a particularly good line. The 13 versus 31, as in how did I choose with the dice? Is that Shubham's question? Oh, I've got a big dice and I've got a little dice, and I use the big dice for the first number and the little dice for the second number. It's just something that's clearly random. Of course, you wouldn't do this on, but I've only got 36 data points in my data set. If you've got a bigger data set, then you wouldn't actually do this by hand. You'd probably use a computer. Theil-Sen you can do by hand because it's pretty efficient, pretty easy to do. Yeah, so that's RANSAC. And RANSAC has some really nice properties. As you saw, it found the optimal line even in the presence of a lot of noise. And that's in contrast to, say, ordinary least squares that would have had no way of making any sense out of this data set at all. It would have tried to minimize things that weren't there. Normally, Theil-Sen works quite well as well. Okay, just take a few seconds and I'll start sharing my screen again so that I can see what's going on. Right, let's have a look at some code. And this is far more hideous code than it really needs to be. There's really only 2 lines of code here that you want to look at, and the rest just run away screaming for the moment. I will come back to this. I'll use these back on the Sacramento examples, and then you'll go, oh, yes, that's really super easy and obvious. By the way, if I sound a bit distracted, my hands are filled with blue tack and little pieces of brown string and everything's everywhere. Okay. So in the same way as we had the sklearn linear model ordinary least squares regressor, nearly there, just get my camera in place. We just introduce a Theil-Sen regressor or a RANSAC regressor. And then if you remember, we had this fancy linear plot kind of thing. Let's have a look at what it did on that same data set that we were looking at before. They're both really spectacularly good. So with the RANSAC model, it will find, I think it's 0.1 and 0.6 here, and find that the line going through that happens to be really, really close to lots of points, and therefore declare that to be the perfect line. And with Theil-Sen, even if you do all 56 possible pairs, you end up with 8 lines that join up to this weird point, outlier point. But the other 48 are all basically in this same space. So the median one ends up looking about like that line there. I think that's the line that goes through 0 and 7, I think it is. So they have their own. Yep.
So what does the algorithm use to decide which ones are counted as outliers versus the inliers for RANSAC? Do we specify the distance?
Yes, you specify, yeah, with RANSAC you specify the distance as to what's considered close. And with Theil-Sen, the only thing you can really specify is how many iterations do you want to do. And it'll default to something large enough that it gets pretty good numbers. Okay. So Theil-Sen and RANSAC have their own meaning for what best linear model is. So if we now look at the the ordinary least, the R squared score of these, it will actually say that it's doing quite badly. So you see this same graph that I did up here, where you look at that and go, Theil-Sen and RANSAC are obviously doing great, and ordinary least squares is obviously wrong. If we then go and ask, what was the sum of squares distance? Well, of course, ordinary least squares did give you the smallest sum of squares. I get 14,166, which is worse than RANSAC or Theil-Sen, because sum of squares says the best line is the one that minimizes sum of squares distance. So of course it does that, whereas these other algorithms have other meanings to what is the best line to be fitting through some data. And now, with 31 minutes left to go in the session, let me introduce you to the actual tool that you use a lot if you're doing this seriously. And that is Huber. Yep.
Thank you. Sorry to interrupt. I mean, just to understand it. I mean, if we have the outlier, then of course the Theil-Sen and the RANSAC model is good because it focuses more on the median line. Because ultimately, if there is something, we prefer median. But if the data is does not have outlier, did we try to focus more on mean, something like that?
It's not just whether or not the data has one big outlier. In order for the least squares algorithm to be the best thing to do, the errors have to follow a normal distribution. They have to be symmetric, so you're as likely to be as above as below. It has to be that the probability of something being a long way away drops off with e to the minus x squared, where x is the distance. And so there's a whole bunch of other assumptions that are made in order for the least squares algorithm to be the best way of doing things, that it's actually incredibly rare. There are really two cases. One is you have very few data points and lots of columns, in which case you do regularization. Or you have lots of data points, in which case there will be some crazy stuff happening. There will be some outliers. There will be imbalances. There will be noise, in which case you'll need to use one of these robust regressors. It's very, very, very rare to see least squares on its own being a good strategy.
So, Craig, just to understand more, sorry, from the text perspective. So first what we have to do is try to do the distribution curve, get the distribution curve, if it is a normal distribution curve or not, whether it is left to right distribute, and how exactly it is plotting up. Then we will see how that way it will give us some sort of data understanding. And based on that, we can apply some of the regression model. Is that how we proceed? I mean, just to understand some data.
You could do that. That would be a much more careful approach compared to what generally happens in industry. What generally happens is you look at the shape and go, short and wide, regularize, long and narrow, robust. And you can do that just by looking at the shape of the data frame without looking at the distribution of the data frame.
Can we try it? I mean, later on, not now, but after.
Sure, absolutely. Yep. Okay. Last in the toolbox is Huber. So what Huber does is it says, if a point is a long way away, then we just use the absolute value. If the point is close, then we just use the square. So if you've got no really bad outliers, then Huber gives you all the same capabilities of least squares. If you do have outliers, the outliers don't penalize very much, but the line will adjust to sort of accommodate them. And so almost always you'll find that this one absolutely kills everything else for accuracy. So you can barely see the impact of that outlier. I mean, that line is just slightly above the 1 and slightly above the 7, where I think 1 and 7 is what the Theil-Sen algorithm actually went through. So it's just a teeny tiny bit higher, but barely able to see. So the only parameter you need to put in here is when do you want to stop being a squared difference, which is what all these points are experiencing, versus what do you want to have as an absolute value addition. And then you just throw Hoover in, and that usually produces better results. So, summary of when to use this. Hoover's usually going to be your first port of call. It almost always works. It almost always works really well. Theil-Sen is really good if your X values have errors and noise. So if you can't measure the things that are in your data frame very well, and so you've got uncertainties there, Theil-Sen kind of copes with that because, well, I'm just randomly picking points anyway, so and a little bit of error here, a little bit of error there won't matter. And it can cope with anything up to, somebody's calculated this, 29% of the data set can be completely garbage data with no relationship between the X and the Y, and Theil-Sen will still be able to work with the other 71%. RANSAC is even more robust and can cope with anything up to 50%. So let's pop back to our other data frame, our other notebook. He says confidently, let's go back to our other notebook. Sorry, I'm just having troubles. I've got this sort of silly thing on the top of my screen that prevents me from being able to get to the tabs easily. Let's see if I can, give me 1 second and I'll be back again. Right, so what we did here was, so I'm now back on the simple linear model from the Sacramento data set. And now I'm going to look at trying some other estimators. So let's insert a cell below. I really like the Theil-Sen regressor just because it's fun and because you can do it by hand, and like if you ever have the situation that you're working in like a relational database and you've got no tooling to support you doing any data science, but you still need to do some kind of a regression problem that you think might be linear, you can actually do Theil-Sen in Siegel. You can use subsamples of the table and loops and things like that. You can get this quite fun stuff to work like that. Okay, let's have a look at Theil-Sen and how it's performing. Right, now just as a reminder, we're printing out the median absolute error. So this is how 50% of the time we are within this distance of the correct answer. So 41,000, and here's our mean, 54. And maybe I should copy some of this stuff into Slack. Let's go back, ordinary least squares. It was right to within 86,062. So let's pop that into Slack. Actually has a very good question that I will answer in a second. So ordinary least squares was 86062. Then the dummy regressor did better still, which was kind of a bit sad. Then we improved on that with the lasso model because the lasso model didn't focus too heavily on just individual data points. And so individual columns were not necessarily overly represented. And Theil-Sen seems to be doing even better still. So let's copy that one. Theil-Sen managed to get that down to 41,000 error. Akshay's question, how do you stop yourself from overfitting when you give the minimum distance? Actually, is that a question about the Huber model or about the RANSAC model? Or
Those are the RANSAC.
about RANSAC. Okay, about RANSAC. How do you stop? This is a long answer, and we will go into it in more detail on Monday next week, which is we can tune hyperparameters by taking a subset of the test data, sorry, the subset of the training data, and try different values. So you'll know whether you've got the distance right if on your subset of the training data that you then compare against a little bit more of the training data, if it's really good at predicting that leftover training data, then that's a good model. And then you can evaluate that by looking at it, how well it went on the actual test data. That's probably not a super helpful answer. I'll give it another way, which is there are processes that you can do to try and find the right number here. Did that sort of answer the question in a not very good way?
Sort of. So we're basically increasing the outsample, and instead of creating two sets, a train test, we're creating train 1, train 2, and a test 3. Well, a test.
Yeah, it's actually called cross-validation, and you can do hyperparameter tuning in the cross-validation step, which we'll do in the next lesson.
Okay. All right. Thank you.
Okay. Theil-Sen works quite well. You can cope with vast amounts of data at very little effort. Let's look at the same thing with the RANSAC regressor. Now, the RANSAC regressor is just a teeny bit different in one place, and that is in all these other linear models, they've had an intercept parameter and a coefficient parameter. What happens with RANSAC is there's a field called estimator, and the estimator inside RANSAC has an intercept field and a coef field. If you think about it, it makes a lot of sense, because RANSAC, it draws the line and then it sees how close is that line. Well, that's the line that it's drawing. There's an ordinary least squares hiding inside RANSAC as it finds the best line through 2 points, goes through and calculates how good that line is and how many points it got near. Oops, and I've got to make that a RANSAC regressor. RANSAC regressor. And if you look at that one, I haven't fiddled around the tuning of that parameter that Akshay was asking about, but it still managed to produce pretty reasonable results, even with just raw, mindless stuff that I've got at the moment. So how did that go? I think that actually was slightly worse than, no, it beat the lasso, but it didn't beat Theil-Sen. Right, last of all, same thing again, but this time let's use the superpowered one that generally does the best. That's the Huber regressor. If you're on a very old version of scikit-learn, this was only introduced in like version 20. And just to make my life miserable, didn't do all that well. The median absolute error was still, not all that amazing. I'm having a bad day with Theil-Sen today. Theil-Sen did badly on my example on the table where it did worse, and now when you actually put it into code, Theil-Sen's beating absolutely everything else. But what you do see is, if you have a look in the Slack channel at the sort of numbers we've got here, we have ordinary least squares coming in very, very poorly, even doing worse than just a single dummy. And then we start doing regularization because we think we don't have enough data, and that improves things. And then we throw regularization in, and that gets us, it halves the error that we were facing when we're using ordinary least squares.